Buenos días, bienvenidos y gracias por asistir al acto de defensa de la tesis doctoral titulada Membranas novedosas de matriz mixta y sistemas PSA para la recuperación de hidrógeno residual industrial, la cual ha sido dirigida por el profesor Alfredo Ortiz y la profesora Inmaculada Ortiz. Esta tesis se ha llevado a cabo en la Universidad de Cantabria, más concretamente en el Departamento de Ingenierías Química y Biomolecular, en el grupo de procesos avanzados de separación. Todo ello en el marco del programa de doctorado en Ingeniería Química de la Energía y de Procesos. La tesis ha sido financiada por diferentes proyectos europeos y nacionales y cuenta además con un contrato predoctoral FPU, del cual se realizó el mínimo de 90 horas de docencia. La tesis ha dado lugar a 7 artículos científicos, 6 de ellos como primer autor, de los cuales 2 de ellos se encuentran actualmente en preparación o en revisión. Además, los resultados se han difundido en 16 congresos nacionales e internacionales. Durante el periodo de tesis ya se han llevado a cabo también otras actividades de divulgación y de formación y obtenido reconocimientos en diferentes certámenes. Además, con el objetivo de cumplir los requisitos para optar a la mención internacional, se realizó una estancia predoctoral en el grupo LEPAVE de la Universidad de Luporto, bajo la supervisión del profesor Adelio Méndez. La tesis doctoral cuenta con el visto bueno de 2 evaluadoras externas, la doctora Rosa Guadalupe de la Escuela de Ingenierías Química e Industrias Extractivas y la doctora Liliana Tomé de la Universidad de Coimbra, la cual además se encuentra presente como miembro internacional del Tribunal de Tesis. Y desde ahora en adelante hasta finalizar la presentación se llevará a cabo en inglés. This is the index that will be followed during the presentation. First, an introduction about the motivation and objectives of the thesis. Then, 3 main research topics will be addressed. And finally, some insights about the main conclusions and recommendations for future research will be given. Thus, the first part will be the motivation and objectives of the thesis. The industrialization and population growth have led to a twofold increase in the energy consumption, while the worldwide demand remains dependent on fossil fuels. Although renewable energies such as wind or solar delivers the lowest electricity costs, they are intermittent, which highlights the need for a sustainable energy vector as hydrogen in order to balance the mismatch between generation and demand. In this sense, hydrogen is not only capable of producing energy, but can be used in a wide range of applications, giving rise to the hydrogen-based economy. Hydrogen can be integrated into the energy system and they use in mobile or stationary applications for power and heat generation and also as a feedstock in the industrial sector, which is currently the main use of hydrogen. As it can be seen in the figure, ammonia, refining and methanol are the main hydrogen consumers. Due to its use, various hydrogen industrial waste gas streams can be identified. For example, in the case of the ammonia and methanol production, a fraction of the unreacted part cannot be recirculated into the reactor in order to maintain the optimal operating conditions, and thus the methanol and ammonia poor gas are identified. Moreover, hydrogen-containing streams can be generated also as a byproduct, as in the case of the steel industry, in the case of the cocoa gas. Thus, these streams represent a potential need for hydrogen recovery and highlights the need for a hydrogen purification unit in order to reach the purity target of the different uses. In this sense, cryogenic distillation, pressure absorption, and membrane-based processes are the main gas separation technologies, and this thesis is focused on the latter two, since the high energy consumption and capital investment related to the cryogenic distillation. PSA is a major technology for hydrogen separation and is based on the absorption of the different impurities in a package composed of different layers. Moreover, PSA is characterized by carrying out a cyclic operation, mean absorption, the first step. Then, and before the vents become saturated, the column is regenerated by means of a pressure decrease to atmospheric pressure that is called the blowdown, combined with the use of a fraction of the product that is being produced in another column that is called the parts, or by the use of advanced regeneration strategies such as vacuum or centrifuge. Then, and before the cycle is started, the column is repressurized to initiate a new cycle. PAC systems are designed with multiple columns and the key performance parameters are the hydrogen purity and the hydrogen recovery. On the other hand, membranes are a promising technology due to the lower energy consumption and are based on the ability of the different gases to pass through a physical barrier, being hydrogen permeability and selectivity the KPIs. Moreover, different mass transport are associated to the membrane materials. While a molecular shift mechanism is characteristic of the ceramic and carbon membranes due to the pore size, the gas molecules are absorbed, diffused to the membrane thickness, and dissolved on the permeate sites in the case of the organic and metallic membranes. In particular, in the case of the metallic membranes, hydrogen is dissociated at high temperatures, enable the high separation performance. Focusing on application, in the case of the hydrogen recovery from industrial waste gas streams, such as methanol and ammonia parts gas and the coke oven gas, which is the scope of this thesis, two main approaches can be applied. On the one hand, the use of a hydrogen selective membrane, since hydrogen is the main compound in these mixtures, and on the other hand, the retention of the different impurities in a packed bed in the PSA systems. Regarding the use of membranes, since the industrial waste gas streams are typically available at low temperatures up to 45 Celsius degrees, organic materials are selected in this thesis, avoiding the additional energy consumption related to work at the high temperatures of the metallic and the ceramic membranes. Nevertheless, polymeric membranes face some challenges. As it can be seen in the figure, the separation performance is represented by the Robson plots with hydrogen permeability in the x-axis and hydrogen selectivity for a specific gas pair in the y-axis. Also, polymides, that are among the materials that deliver the highest selectivity, a hardening improvement is required in order to reach the target area of the metallic materials. And this can be achieved by the use of inorganic fillers, giving rise to the mixed matrix membranes. Moreover, an additional challenge is related to the process intensification on these polymer-based membranes, in which configuration, such as hollow fibers, that allows a higher surface to volume ratio are required. Commonly, porous materials such as theoretic methyl frameworks can be applied due to the suitable pore size, and in this thesis, CIA8 and CIA90 have been selected in order to enable a molecular shift mechanism in the polymer-based membranes. Moreover, a novel approach using hydrogen storage compounds has been also explored with the aim of enhancing the hydrogen affinity to the membrane. In this sense, the lanthanum nickel alloy has been selected based on its hydrogen storage capacity and the operating conditions of the polymer materials. Furthermore, the process intensification into a hollow fiber leading to module devices has been also addressed in this thesis. Although mature, PSA faces some challenges to be used for hydrogen recovery from industrial waste gas streams. On the one hand, the presence of low adsorbable compounds such as nitrogen and carbon monoxide that requires the use of tailored compounds, the use of regeneration strategies such as vacuum or TSA that increases the hydrogen production, the process, and the influence of the minor impurities that might be present in the industrial waste gas streams that can decrease the lifetime of the beds. As example, hydrogen sulfide might be present in the coke oven gas depending on the coal source, and despite a cleaning process that is typically carried out by MDVA absorption, up to 500 ppm can remain in the treated flow, being a challenge for the subsequent hydrogen separation units. This thesis is focused on the influence of this impurity as well as the evaluation of the vacuum regeneration in the case of the PSA processes. Thus, three main research topics have been addressed. First, the synthesis of mixed matrix membranes incorporating both porous fillers and hydrogen storage compound, the process intensification into a hollow fiber configuration, and the evaluation of the PSA processes in a view towards its future integration into hybrid systems.